Hello everyone. This is a 3D mechanical control system simulator that I've been working on for a while. It has not been completely finished yet, but I'd like to show you what it does. First, I'd like to review what a control system is. If you haven't taken control theory, you might not know what I mean by a mechanical control system, and you may think I'm talking about something way more complex, like a car or a steam engine, but I made a translational mechanical control system, which is much simpler. They're defined as any system of masses and connections where connections can be a spring or a damper. Springs are bouncy and store motion, while dampers are sticky and restrict motion. Masses have inertia and only move when disturbed. Connections can be to other masses or ground, which is an unchanging reference point. These are used to simulate the behavior of actual physical mechanisms, mostly in control systems. For example, a transfer function can be retrieved from a mechanical system, and a controls engineer can design a filter to minimize the vibration of the mechanical system. This project simulates the behavior of mechanical systems by simulating the motion of the masses and rendering the connections. The user makes a mechanical system by specifying where the masses are and the connectors are. They also specify what is connected to what and configure the force inputs of the system. The program will render wires that connect the components, and this allows a user to build a control system with connectors and masses anywhere in space, and they will automatically connect to each other using the wire rendering. When running, positions of the masses are calculated using a statespace matrix. Connectors only allow movement in one direction, X, Y, or Z. A statespace representation is a way to transform a higher order differential equation into a bunch of first order differential equations. These equations are represented in terms of a statespace matrix, state variables, the derivatives of state variables, and inputs. This makes it easier to solve differential equations. You may be thinking, why use a statespace matrix when I can use a classic physics simulation? I can keep track of positions, velocities, and accelerations in arrays and just apply forces to each member of the array. I'd say that using a statespace is nice because the statespace matrix only requires one use of delta time for getting velocity from acceleration, whereas you would need another delta time to get position from velocity in a classic physics simulation. I think that delta time tends to create inaccuracies in simulations, and it's better not to amplify the error of it. Also, the statespace matrix packages the connections data quite well, so in order to calculate all the positions, you just need to do an n by half n matrix vector multiplication. You wouldn't have to parse the connections because the matrix doesn't change. And if needed, a transfer function can be pulled from the system easily. I made this because I saw diagrams in class of control systems and thought they looked nice. I also wanted to see the motion of mechanical filters in systems in real time, and I wanted to simulate a system that can't be simulated before, which is a 3D one. I'm also hoping that one day it is possible to feed in an audio signal to control the position of a mass. This is so I can see a mechanical filter work on a sound signal visually. The audio is probably going to have to be sampled at a really slow rate due to the computation of graphics, but I think it would still be fun to look at. Although my system supports horizontal movement with custom force inputs, I like to make a lot of my examples vertical and have a gravity force input for all masses. This is because it looks more natural and realistic. This program also allows us to change the textures of masses, springs, and dampers if we wanted a better look. To demonstrate this, I'm going to replace springs with dodgeballs because they're squishy, dampers with interlocking arms because they stick together, and masses with rotisserie chicken because chicken has mass. As you can see, it is very unique, quite a different look, and it worked. You can see how the shader tries to make a wire from the texture by extending the ends. Also, there are some visual glitches regarding the connectors. This is because primitives at the back have to be rendered before primitives closer to the screen, so the blending works. This can be fixed by sorting the primitives by depth before sending them to the shader. But that slows down the simulation and it's not guaranteed to work, as connections could intersect each other. For right now, the program won't allow semi-transparent textures. Recently, I added a feature to allow for each mass to have a different texture. It uses a very basic texture atlas where all textures are square and are stacked on top of each other. So accessing them via texture coordinates and texture indexes in the fragment shader is easy. I've given each mass a texture index in the static vertex buffer object, so the fragment shader can choose the proper texture for each mass. Now I'm going to start talking about how I made this project and how it is structured. It is programmed in C, uses OpenGL for rendering, GLSL for shading, and the makefile for building the entire project. I have a struct that represents a connector and another that represents a mass. Each mechanical system has its own struct, which contains other structs for the data of all connectors and masses. It also includes a system state struct. The system state struct contains all components of a statespace equation, but it has been changed a bit, so the unnecessary parts of it are gone. It is set up once the system is initialized and stays constant for the rest of the simulation, unless other inputs are added during runtime. Connectors and masses are rendered separately using two draw calls. The connectors data struct has an array of all the connectors in the system and has two vertex buffers. One vertex buffer is for dynamic data, which contains the positions of the ends of each connector, and the packed integer for miscellaneous data. The other is for static data, which represents the wire component of each connector. These wires don't change because only the spring or damper has to stretch. So the GPU receives 4 points for every connector. The vertices of the rendered connectors will be made by the geometry shader. The geometry shader will create the billboarding effect using a camera and will create the texture coordinates for the fragment shader to use. Currently, I send the fragment shader 2 textures to sample, one for the spring and one for the damper. So how do we texture the wire? Currently, I just use the edge of the connector's texture coordinates. This means a wire is currently rendered as the stretched version of the ends of a connector, which is why the texture test looks so odd. And for now, I render a ground by making a flat wire at the end of a connector's initial position. Moving over to masses data has its own static data for rendering the model of a mass block. It also contains a texture atlas as well as an index for each mass to identify what texture it will use. Masses data shares the same dynamic data vertex buffer with the connectors data, but it only sends one set of connector ends to the GPU. This is because connectors have masses on their ends, and I am assuming that each mass is connected to a unique connector for now. Using this position of the mass, I just instanced the blocks at each position given. This structuring may seem odd, but this system is the way it is because I originally planned to render a connector and one mass in one draw call. I originally wanted to use the geometry shader to add vertices to an instance, but I forgot that the geometry shader doesn't accept chunks bigger than primitives. It could still be possible to do this by rendering each connector and adding 12 more vertices, but that would stay constant in the geometry shader and it would be bad for performance, I believe. So I decided to change it to the way it is now by rendering masses and connectors differently while sharing the same vertex buffer object. This is pretty efficient, but this also means your system needs to have every mass connected to something or it will not render properly. I have shown a lot of examples, but none of them feature a system with X, Y, and Z movement, and here's why. I plan to fully extend my project to 3D, but it will come later. I also have other things I need to sort out. I have a lot of plans for improving this project, and my current priorities are as follows. I want to upgrade the position calculation so it properly uses the statespace matrix. Currently, it uses a cheap and lazy option for testing the rendering of the project. I also want to expand the system to handle 3D systems by grouping the masses and moving groups of masses simultaneously. I want to allow the user to drag masses and input forces while the system is running. I also want to enable them to resize connectors and blocks. I want them to be able to retexture grounds and replace the ground positions. And I want to also let them texture different faces of a cube with different textures. I'm also thinking of adding an editor with that as well. Well, that's all I have for you right now. I hope you like this project and I will provide more updates on it later. See you in the next update.